Hi everyone. My name is Mikhail, and first of all, I would like to thank you that you came here, although it's evening already. Actually, I will speak about lots of technical details. That's why, if you want to understand something, you will have to listen to me very attentively. This is not something that I made up. This is a real case. I'm going to tell you about the product that we create and this scenario and the reason why we had to dwell upon these problems. We create a platform for cloud service distribution and we use it ourselves. It's not only us who use this platform. We are not the biggest user of it. But still, we're aware of all the problems that it has in order to calculate cloud service. For the purposes of billing, we are to calculate these resources to get consumption volume. How does it work? We request external services to provide the necessary information and update it in our system. The biggest customer had more than 12 million lines when a problem occurred. I think that now it has more than 13 million lines. Less than 1% of updates. And updates are not linear. They are based on hierarchy. I'm going to explain it to you. And we also conduct an audit for limits accessing. And there are several threads in updating. What is a hierarchy? We have main seller. It has several smaller sellers. And smaller sellers have end customers. Normally there is one main seller. There are fewer smaller sellers. And there are a lot of end customers. So here is the hierarchy. I can show you the code. It looks like that. We select subscriptions that we have for various applications. For example, Dropbox. It may be Office, Azure, or any cloud service. So we request information from this service. We block this line 3 times. It means that we lock the line for user, reseller, and main reseller. And we check that maybe some of these levels exceeded the limit. For example, reseller can sell Dropboxes for 1 terabyte, so we had to check whether this limit was exceeded or not. If it was not exceeded, we can update. These functions are very important. That's why we conduct special tests for each release. And a normal chart should look like that. So fluctuations in the beginning are not actually important. It's important that this curve does not go down. Absolute values are not as important as relative values. So we can see that it's quite flat. These are records per minute, numbers of renewed subscriptions per minute. So everything is okay. It's a normal chart, but once my colleagues came up to me and said that they had a problem, and our normal chart, well, you can see it in orange the way that it should be. We saw that this chart went down. We processed more than 250 resources in our Go chart, and here we had 160 resources during 3 hours, and we didn't know how long we would have to wait, in this case maybe for several days. And after that, our research showed that within 10 minutes, we have plummeted by 50%. So we needed to find the reason why it happened. We looked at the chart. Maybe there was a problem with the server. Well, there was no such problem because the chart showed no unusual loads. Everything was quite okay, no problems. One more thing, we tried to reproduce the problem at once, but it was not reproduced. So this was a fluctuation problem. The problem of the basis setting, well, it was quite possible, but the base was not changed. So at first, this test was okay. After that, it was not. After they tried to reproduce it, there was a problem again. Auto vacuum. Well, we did not manage to link our problem with auto vacuum because auto vacuum was not launched neither before nor after it. And background load, it's an option, but we excluded it because on the chart there is no additional load, so this is not the reason. But actually, when starting this point, this reason, we realized how it was possible for the chart to degrade. We realized what the problem was, and then we managed to reproduce it here. But this is an extreme case, so you ought to open a transaction, create a table. You do not have to create a table, actually. You can do update or anything, but transaction should be opened. When we write begin in Postgres, transaction is not opened yet. We need transaction to be opened in Postgres. That's why we conduct any operation after begin, so the transaction is opened. So why did we decide to use create table? Because it creates no load. It does not lock any business tables because business is not even aware of this table. It has just been created. And it can be launched in a different base. So, if we understand that Postgres is a cluster of database, then we can create two databases in one cluster, open transaction in a different base, and our database will suffer because of that. So, opening this transaction, we received degradation. So, we thought that it was it. We have found the problem. We thought that we should not use long transactions. But I thought, okay, we can reject long transactions because we know that in that case a report was launched, but we do not know what the customer will have. If they launch something during 5 minutes, is it long or not? How much productivity will we lose in that case? So we do not really understand why it happens. And we tried to understand what the problem was. In order to understand it, we will need to understand how Postgres stores data. Physically, I mean, how it stores data on the drive. And we need to understand how transactions happen. So what do we have? We can reproduce the problem. We have Postgres 9.6, so it's the latest version. And I don't know whether this is a bug or not, because I talked to Bruce today, and he said that it works like this. So we have the application activity log. Using that, we can see what functions failed. Speaking about disadvantages, background activity of application. Something is launched in timer, it can create load as well. Java and Hibernate are used. So maybe Hibernate does something wrong, and actually it would be great to eliminate these disadvantages. That's why we changed the functionality into the base. So, we address someone in order to get the result, we generate a random number, we log 3 entries, and we update 3 records. Actually, this verification is not important here, and real one will not have any impact on the results. In order to understand what code entry is slow, to understand where the degradation occurred, I used timestamps. These are not breakpoints, these are timestamps. So I created a set of 2 values. I fixed time and a text word that I used in order to understand what this point of the set corresponds to. I numbered them, there are more than 30. And the chart looks as follows. Actually, this is the chart of emulation procedure. Before that, I updated the resources many times. And remember that chart with degradation, it's closer to the end. And here we can see that degradation happens from 0.5 to 0.6. And after that, I realized that this is select for update. So we lose 90% of time here. But we do select for update 3 times. And from 4 to 5, from 5 to 6, from 6 to 7, all of these steps are about select for update. And step 2 takes a lot of time. Sampling by primary key. So it's good that we realized where we're slow, but we do not understand why we're slow. And we go even deeper. So I'm not going to tell you about transaction and what a transaction is, because I think that you work with database for a long time. We are to understand how Postgres complies with asset requirements. We're not going to speak about durability because it's not related to our topic. Atomicity, consistency, and isolation are to be considered by us. Postgres uses MVCC for these purposes. This approach is used not only by Postgres but by Oracle as well, but implementation is different here. We're going to speak about implementation later. What are the advantages? Writer does not block reader. Reader does not block writer. Everyone works in parallel, and everything is all right. But there is a price that you have to pay for it. One of the manifestations of this price is that we have to use auto vacuum to clean the block. And there is one more thing here. Let's take a look at a table in Postgres. It's a file on a disk. In PG data, it consists of pages. Each page weighs 8 kilobytes. This is quite a deep setting. And normally this setting is not changed. The page has a header, a pointer, several pointers, and data in the end. So, data have their headers as well. It looks like a title, bitmap, OID, and user data. And speaking about the header, there are more than 20 flags here actually, but for us there are 2 important aspects: txmin and txmax. Txmin is the number of transactions that created this line. Txmax is the number of transactions that deleted this line. And how does it work? Well, we created a table we inserted an entry there, and we have 456 for txmin. It's the number of transactions. After that, we conduct update. For the old line, we have tx marks, and for the new line, we have a new entry that has txmin that corresponds with the value of updated transaction. When they say that update in Postgres is about delete and insert, we can say here that it's true. So the previous line is deleted and a new line is added. Everything is okay in this approach, but transactions can roll back. Still, the entry that the line was deleted is filled in, so we open transaction, delete, and roll back.
So for the second line, dsmax wrote itself, like we deleted it. However, we know that we found this transaction and it's not deleted. This is commit log, which is basically massive of data where key is transaction number and the status when it's ended. So if we look at our previous actions, it will look like when we make insert, it puts the line and it writes in the log that this transaction is completed. Then it's updated and committed. We open new transaction, begins. It's deleted, and in the log there is a record that this transaction is in progress. And then we write status aborted for the transaction. So there can be three statuses: committed, in progress, and aborted. There is also a fourth status, but I've never encountered it. I think it's subcommitted, but it's really never used. Okay. Now we know how to read lines. We understand how they are calculated and processed. We just need data for multi-user work. But Postgres allows it to open several sessions and to ensure synchronization of data at the same time. It's simpler to show based on example, but basically a transaction snapshot, it means in theory it's condition of all transactions in the systems, but in practice when we open transaction, the first line, select txid current, we know our current transaction, and next line means the text representation of our transaction, and it tells us the following. There are three values. The first one tells us that all the transactions which occurred before this value are inactive, which means that they are either committed or locked, and we can see the table which relates to this transaction. The next value, xmax, means that all transactions, including this one, are still active in the system. So maybe they are for the future or unknown, and we cannot interpret this value. And the third value is the list of transaction numbers between xmin and xmax, and they are also active. And we cannot interpret them because they are active and we don't know how they will end. So as a conclusion, there is algorithm for determination of lines visibility, like you can see on this slide, on this diagram here. Maybe these are not even all of them, but just the major ones. For example, we can take the first two lines, how to interpret it, so you can understand what we've discussed previously about MVCC. So let's have a look. The X means status. If it's aborted, then it means that the line was created in transaction and then it was rolled back. This is why the X means status is aborted and we do not see this line. Next line, in progress. It means that this tuple is being created right now. We're checking if it's our transaction. No, it's not ours. So again, we do not see this line. It's created by somebody else. When we check again, if it's Xmax, then it means that we created this line, then deleted it, and we do not see it anymore. And if we see it, then it means that we created it and we're working with it currently. I will not go in detail, but basically MVCC works like this, and this way we ensure stability and synchronization. And now we will move to the next part about the degradation of transaction. So again, what was the problem? This query started to slow down, and we will look at the indices next. So how indices works? Okay, we have a certain index. Index shows index and block. And when we update the line in the table, it creates new tuple, new index, new link, etc. So basically the number of indexes increases with updates. Also, maybe you've heard about hot updates. If we update a line which is not indexed, so why we should rebuild it? We can economize on these operations and just tell the system that if somebody asks for this index, just look there. In this case, index doesn't change, but inside tuple it's redirected. And in this way we can economize on updates and win a few milliseconds. And then it will go further in this manner. Also, there is another optimization as mini vacuum or single page cleanup. It's undocumented, unfortunately, but this is something why we had problems. So how it works? Index has a link to the link in the block. Let's say the block is completed, and then we need to create a new block. And we need to create a new link in the index, which is not very good from one side. And on the other side, why do we need to create a new block if maybe we can clean up the data in the current block? And we can discover that in order to perform this, to execute this update operation, we can maybe clean up the existing block, and we can clean it up. If there is no other transactions, we just clean the current block, and in the index we add a link there is a redirection to another index, and then we start to fill it again. We start to fill it. And the problem occurs when there is a long transaction. On the one hand, it's optimized, but on the other hand, it must be as fast as possible. So there should not be any unnecessary actions. And the checkup of these blocks is executed in the following way. We're doing transaction snapshot, and if there are lines which were deleted before the first xmin, we can delete them. But if we have a long transaction, then it means that we need all the lines, and we need to create a new block and to fill the new block. Now we have two links in the index for two values. Then the third comes up, fourth, sixth, seventh, etc. And at the end of the day, we end up with the situation when for one value we have 16 references from index to heap, and we need to analyze 128 tuples. It's just this one example, just 6 tuples per block, and in reality it can be much more. It depends on the length of the line. And for those who like to do some homework and some experimenting, this is how you can recreate this situation. We create a table, we insert a line, turn on the auto vacuum, and start the begin transaction. And then we forget about this session. This is our long transaction. And then we start the update. The minimum. Yes, so how we can check that we have a problem? We write select count, explain analyze, and exactly in this case explain will show the number of links from the references from the index to heap. In this case there is just one because I haven't started updates yet, and the time of execution is 0.058 milliseconds. And when we start the script, in 5 minutes we will see degradation. It will become 2 milliseconds, and then more and more. In 20 minutes it's already 6 milliseconds degradation. And based on the number of updates we can see, and even we can create a graph. This is a linear graphic diagram, and for each 10,000 updates we lose 56 milliseconds. With my number of tabs. And if we create a long line, then block will be filled up faster, we will get more references and faster degradation. Also, what we can take into consideration in comparison with the initial speed, already after 10,000 updates, the speed will get significantly slower. So what are the conclusions? To summarize everything. If data doesn't change, then long transactions is not a problem for you. If data changes but distributed evenly, then it may be a problem if you will keep it for 1 month or maybe 1 week, but it depends, and probably it will not be a problem related to mini vacuum. If your data changes actively and often and speed is important for you, then you will get this problem, and you will have to tell to your customers not to use it, not to use such long transactions. If you cannot remove this, then you can maybe move it to replica. I also gave a link to YouTube. There is an interesting video about this. And the last item, what we did, for example, we cannot create a replica, and nothing will prevent the user from long transactions. Maybe he created some report, and in 10 seconds degradation will be already significant. In this case, we can try to reduce the side effects. So the problem is that we update and we have customer, seller, and reseller, and if the problem is on the second stage with the reseller, then we can maybe reduce the number of updates and reduce the number of created tuples. So if we have more than one customer, then we maybe can group them and make just one update. And in such a way we can reduce the load. And the degradation was significantly decreased. If you look at the first line, 50,000 subscriptions without long transactions, the average speed of processing was 135 milliseconds. And then it degraded to 59 per second, so more than 2 times degradation. When we're talking about size of batch, let's say we're taking 10 customers, process them, and do it once for a reseller. The degradation is much less for the same number of subscriptions. What else is interesting? If we create a very big batch, then average speed will decrease, but it's not related to mini vacuum. It's just related to the fact that this resource is a hot resource. And if we keep it for a long time, in order to process 10 customers, we need to spend more time. And if we keep it longer, then the rest will have to wait for resources. So it will depend on the performance of the hardware, memory, hard drives, and the bulk size. So we need to find some golden rule which will ensure the optimum speed. That's it. Thank you very much. There is a question. Is there any questions? Yes, my name is Konstantin. Thank you for your presentation. But I have one more question. Reindex will save the situation or not? Thank you. No. Because your references, you will have to have them because the system doesn't know if it can delete it or not. it will not be clear based on what to delete these references from the index and from the table. I should suggest this to Bruce. Maybe it can be developed. And we need to ensure that the procedures work fast. And in case with vacuum, we could make it more complicated and to perform analysis if these lines are not visible in the system. We should address to each transaction to look at its status, and maybe some stages will not be available, and just to delete these transactions from the system. We should discuss it with Bruce. My name is Nurlan. Good evening. My question is about Postgres. So Postgres stores all the requests and then sends it as a bulk request to the system, or it sends it one by one. There is such thing as a log in Postgres, and after every commit, data goes there. So if we go deeper in detail, Postgres has a feature, it's commit delay maybe, I'm not sure. One of parameters which allows user to delay every commit for a few milliseconds and to accumulate changes to copy them in the system later. It drops the data in the data file, but when you execute commitment, then the data goes to the log. And this is related to durability. Thank you for your presentation. My question is, in the very beginning, you mentioned you created transaction and table, for example, and mentioned that it will lead to degradation as well. The question is why? No, it's even further, in the very beginning. Yes, should be somewhere. Yes, this. But this is it? No, but you created a new table, so why? That's right, this is what's important. This is why I wrote that even in the other database we can create a table and it will lead to degradation as well. It can be either in other database and you will think that everything is fine, but actually not. It will lead to degradation, despite the fact that there is no direct link between those two transactions. You will get degradation in the end anyhow, because lots of links from the index to the table will be created, they will have to be analyzed, and you will have a problem. Have you experimented with partitioning while you tried to solve this problem? So the lines from different levels would be in different partitions, and for the end users, they would never go in the same block of data with the data of higher level. I think I understand the question, but the question is not on the side of the client. We update them just once, and Every client has a tuple. It's not a problem. The problem is that the same task of higher level is updated. Yes, exactly. This is the problem. So not just several entries in one block, but one line will be duplicated many times. But when I update both customers and sellers, it will make the situation worse because the block will deplete faster. But the core of the problem is that I update the middle level several times, and then there are lots of references to it in the index, and we will have to analyze it with a diagram. So let's say we're doing 10,000 updates, and such example which you showed at the homework slide. Yes, exactly. This is exactly the problem. You can start it even right now, and you will see. Yes, it's clear. Thank you. Thank you.